This is chapter 12, video assignment number 1. The problem states, at an elevated temperature, NO2 reacts with CO, producing CO2 and NO. That's this reaction here, and it's balanced. It then says there are two proposed mechanisms for this reaction. In one possible mechanism, products form directly from a bimolecular collision that directly transfers an oxygen atom from NO2 to CO. Part of the question is it asks us to devise the rate law for each mechanism. We're going to do mechanism 1 first. So this is the whole mechanism. It's the bimolecular collision. It's just an elementary reaction. And so from that, we can devise the rate law of K equals reactants, concentration of reactants at equilibrium, and concentration of CO at equilibrium, with M and N being the order of the reaction. Now, since this is an elementary reaction, we can simply take the stoichiometric coefficients from the given equation and plug that in for our M and N, making the rate law K equals concentration of NO2 equilibrium to the 1 and CO concentration at equilibrium to the 1. That's the rate law for mechanism 1. And the reason we can do that is, again, it's an elementary reaction, so we're just using the stoichiometric coefficients because we're not given any experimental data to devise experimental M and N. We have to go based on the information given. For mechanism 2, it states that there is another possible mechanism in which two nitrogen dioxide molecules collide in a rate determining step to form NO and NO3, and then there's a second, much faster step in which the nitrogen trioxide molecule collides with carbon monoxide molecule to form the products. Now that is what's written out here. We have our two NO2 reacting to form a nitrogen trioxide and a nitrogen oxide. This is the rate determining step because it says that it's the slow step, and then we have the second step here. Now, the rate law for this one doesn't include both of these. It only includes the reactant from the slow step because that's the rate limiting step, and so that's what's going to limit the rate of the reaction. So the rate law then becomes K equals concentration of NO2 at equilibrium to the M. Again, since we don't have any experimental data, we're pulling from the stoichiometric coefficients, and that's 2. So that gives us this rate law here of K times the concentration of NO2 at equilibrium to the second power. Those are the rate laws for each mechanism. Now it asks us to design a simple kinetics experiment to distinguish easily between these two proposed mechanisms. So the experiment that I would devise is using the rate laws for each mechanism. We would react NO2 and CO in a single container, and we would change the concentration of NO2, and we would change the concentration of CO independently of each other. So when we were changing NO2, CO would be constant, and if we were changing CO, NO2 would be constant. Now, the results, if this was the correct mechanism for the reaction, we would see a change in the reaction rate changing either one of these concentrations. If we changed NO2, we would see a change in the reaction rate. If we changed CO, we would see a change in the reaction rate. That would mean that this mechanism 1 is the correct proposed mechanism. For mechanism 2, it would be a little differently. We would still react NO2 and O2 just the same, but we would only look at the change of NO2. And the way that we could determine this is in the second experiment, if the mechanism 2 was the correct mechanism, we would see that only changing the concentration of the NO2 would cause the reaction rate to change. If we were to change the concentration of CO, nothing would happen to the reaction rate because it's not in the rate law, because it's not in the rate determining step. And so therefore, if in the reaction, changing the concentration of CO changed the rate law, we would know that it was mechanism number 1. If we were to change the concentration of CO and the rate law or rate of reaction did not change, then we would know it's mechanism number 2.